Hello students, this is lesson U4A01. By the end of the lesson, you should be able to say I can find sums of the measures of exterior angles and interior angles of polygons. So let's just recap what we've talked about thus far this year. Okay, in Unit 1, we talked about points and lines on a regular plane or on a coordinate grid. We talked about in Unit 2 ways in which we can transform different objects, okay, through this understanding of rigid motions. And then in Unit 3, we talked about the simplest closed shape, closed two-dimensional shape, which is a triangle, and the different types of triangles, classifying different types of triangles, and then proving whether or not two triangles are in fact the same. And in this unit, what we're going to do now is we're going to start off by talking about polygons, which is just a two-dimensional figure, okay, with multiple sides, more than three sides. In Unit 4, however, we are not going to focus heavily on polygons, but more specifically, we are going to focus on quadrilaterals. But being that this is the first lesson, where we're going to talk about a closed shape having more than three sides, it is appropriate to talk about polygons in general. So what exactly is a polygon? A polygon is a two-dimensional shape with more than three sides. So first one right here, okay, we can think of a polygon in two different ways. One is a polygon that is convex and another one that is concave. Can you spot the difference between a convex and a concave? Or articulate the differences between a convex and a concave? If you're noticing here that this angle H, is what distinguishes a concave polygon from that a convex polygon, then you're absolutely right. So a concave polygon is a polygon with one angle having being greater than 180 degrees. If you notice, right, a straight line has 180 degrees, and in this case here, the angle bends towards the other way. So this is a concave polygon, and it has greater than 180. All right. So we can talk about polygons being regular, and then we can talk about polygons being irregular. So a regular hexagon is a six-sided shape where all the sides and all the angles are the same. Okay, so all of these segments here have the same angle, have the same length. And not only do they have the same length, but they also have the same angle measures. That's what makes this a regular hexagon. Compared to an irregular hexagon, all these sides do not have to be the same length. Some of them could be the same length, but not all of them have to have the same length. All right, and this is it. And this is what we call an irregular hexagon, which is convex, or a convex irregular hexagon, whichever way you want to put it, it's all the same. Okay, so this is an irregular hexagon, and it's also a concave. It's concave irregular hexagon. So a regular polygon, one can define it as all angles and sides are congruent. An irregular polygon is simply not all angles or sides are congruent. And then we can talk about different types of polygons. Okay, we talked about a triangle already. A regular triangle is an equilateral triangle. An irregular one, it could be an isosceles, it could be a scalene. We can talk about quadrilaterals. Okay, a regular quadrilateral is, again, all sides are the same. What kind of shape is this guy right here? That's right, it's a square. We can also talk about a four-sided quadrilateral that's irregular. We can talk about regular pentagons, regular hexagons, and regular octagons, okay? And all of them will have all the sides the same and all the angles are the same. An irregular polygon, irregular quadrilateral, irregular pentagon, irregular hexagon, irregular octagon, all of them, all of these polygons will have different length measures and different angle measures. Okay, so what is the sum of interior angles in each polygon, and let n represent the number of sides? So the best way to think about, or the best way to figure this out, or when we're studying any subject matter or any topic, okay, we want to know as much about that particular topic as possible. So if we're studying polygons, okay, it would be nice to know some information about their angles. So right now, okay, up until this point, we've covered this fact, right? We've proven this as well, that in a triangle, regardless of it being a regular triangle or not, okay, what we recognize is the angle measures inside of a triangle is 180 degrees. It will be 180 degrees. Here, the next figure, we have a irregular quadrilateral. The four sides are not congruent. So, but the thing is, what it will be the measure of all the angles added. If you recall in a proof from Unit 3, we proved that a triangle had 360 degrees, had 180 degrees by drawing a pair of parallel lines and then showing that the alternate interior angles added up together must add up to 180. Now in this case, okay, for us to show why a quadrilateral will have, whatever the sum of the angles are, we're going to do something a little different, however, just as clever though, okay? Recognizing that a triangle has 180 degrees, what we can do is we can pick one corner of the polygon, and what we do is from that corner, we draw a diagonal to the opposing corner. And in this case, there's only one diagonal that I can draw. And by doing this, okay, what we have now is we've constructed two triangles. And looking at this, okay, I don't know what the individual angles are, but I do know that in two triangles, the sum of all the angles in both triangles should add up to, right, 180 times 2. It's 360. This should be 360. So therefore, any four-sided shape will have all the angle measures add up to 360. We can use a very similar technique, okay, where we can again pick one corner of the polygon and again draw the diagonals connecting to the opposite corners. And here I noticed that immediately. Here we have three triangles. So for a pentagon, regular or irregular, convex or concave, all of these any pentagon will add up to having 540 degrees because 180 times 3. Similarly, I can do this, okay, pick one corner and make the connection. I can see now that in a hexagon I have 4 triangles. So because I have 4 triangles, this is going to turn out to be 720 degrees. And then lastly, in a 7-sided figure, okay, I have 2 for 5 different triangles, and 5 triangles giving me 900 degrees. If you were to come up with an equation to describe the sum of all the interior angles, okay, based upon this pattern where n is the number of sides. So for n is equal to 3, we have 180. For n is equal to 4, we have 360. For n is equal to 5, we have 540. For n is equal to 6, we have 720. And for n equal to 7, we have 900. What would be that equation? Pause the video, see if you can figure that out. Hopefully, you had some time to think about this, okay? And maybe perhaps you were able to come up with this equation. So the sum of the interior angles happens to be 180 times n minus 2. So this is actually a formula we are going to be maximizing our understanding. So the sum of all interior angles is 180 times n minus 2. All right, so what is the sum of the exterior angles then in each polygon? To figure this out, let's establish that interior and exterior angles will always form a linear pair. This is going to be our working definition, okay, for what an exterior angle is. So these diagrams right here, okay, all of these angles on the outside, we refer to them as the exterior angle, which is different from maybe perhaps what you may have originally thought. So say if I have a triangle right here, the exterior angle is not the full angle on the outside. It is not that. So again, one more time, an exterior angle is the angle that forms a linear pair with the interior angles. This is how we define what an exterior angle is, okay? So how many linear pairs do you see in each of these diagrams as a result? Looking at this, okay, I see that there are 3 linear pairs here. Here there are 4 linear pairs. Here there are 5 linear pairs. So therefore, okay, each of these angles on the inside, okay, if I add them all up, both interior and exterior, I'm going to have 3 times 180, 4 times 180, and 5 times 180. Again, this is the sum of both interior and exterior. So, wait a minute. If n times 180 is the sum of the interior and exterior angle, and my goal is to figure out the sum of exterior angles, this is just an algebra problem. I can then say sum of the exterior angles plus sum of the interior angles equals to the sum of the interior and exterior angles. And we have expressions for 2 of the 3 things here. We have a formula for this because it was developed earlier, right, in this lesson. We also have a formula for this thing because it was developed in the previous slide. It's 180 times n. So wait a minute, let's just figure this out. Let's just substitute this in. I want to call this guy right here an unknown. We'll call that x. So x plus 180 times n minus 2 is equal to 180n. If I were to isolate x, right, by first distributing the 180 and then subtracting everything over that doesn't have an x to the other side, what I will end up with is x will equal to 360. And this is rather remarkable. I want to maybe just emphasize why this is remarkable. If you take any polygon, regardless of how many sides that polygon has, regardless of whether or not it's convex or concave, regardless of any of those things, the sum of the exterior angles of an n-sided polygon is always going to be 360. That is pretty remarkable. This is going to be a constant regardless of what shape you have. All right, so now with that understanding, okay, we can maybe take it a step further. So the sum of interior and exterior angles theorem, okay, which is what we're going to try and get to, okay, the sum of the measure of the interior angles of a convex n-sided polygon is given by this equation here. It's 180 times n minus 2. The measure of an interior angle of a regular n-sided polygon can therefore be given by this formula here. And then the sum of the measure of the exterior angles of a polygon is 360 degrees. Again, this was what we had developed in the previous slide, right? That the sum of the exterior angles is 360 degrees. So this is the sum of interior and exterior angles theorem. Pause the video for a moment and make sure you have this in your notes. Okay, so what we're going to try and do is we're going to try to figure out what are the angles for A, B, C, D, and E. So looking at this right now, I'm dealing with a 5-sided shape, and according to the formula, I know that the sum of all the interior angles will be 540 degrees. What exactly is 540 degrees? 540 degrees is the sum of all the interior angles. So therefore, now that I have that understanding and I have all these different expressions here representing all the various angles in ABCD, I can then simply add them up and say that's equal to 540. I'm going to perform a substitution. And then I'm going to combine like terms. Subtract both sides by 100 and then divide by 22. Therefore, x is equal to 20. Lastly, I'm going to substitute in what x is back in to figure out what are the angles for A, B, C, D, and E. Well, we already know what D is because D is 90 degrees. So all the angles are going to be 64, 137, 132, and 117. All right, we need to, for this problem, find all exterior angles, okay? And there's some information here that's provided for you. That is, angle 1 is congruent to angle 3. Angle 1 is equal to 3x. And angle 2 is equal to 2x. Pause the video, see if you can figure this out. So hopefully you had some time to think about this. Recognizing angle 1 and 3 are the same. So that means these are going to be 3x and 3x. Angle 2 is going to equal to 2x. And then angle 4 and angle 5, they're both 90 apiece because they are linear pairs, okay, with the adjacent angle, which is also a 90-degree angle. So having this understanding, I can add up angles 1, 2, 3, 4, and 5, and understand that the sum of all the exterior angles must be 360. And then I'm just going to perform all the necessary substitution. So I know that angle 1, angle 3 will both be 3x, angle 2 is 2x, angle 4 and angle 5 are 90 apiece. Combine like terms, I get 8x plus 180 is equal to 360. Subtract 180, divide by 8. I end up with 22.5 as x. So the goal here is to figure out find all exterior angles. Well, 4 and 5 is already known. They're both 90 apiece. Now it's just a matter of figuring out what is angle 1 and angle 1, 2, and 3. So angle 1 is 67.5. Angle 2 is equal to 45 without doing any work. I know that angle 3 should also be equal to 67.5. And then angle 4 and angle 5 are both 90 apiece. So to find the measure of one exterior angle of a regular octagon, okay, how do we go about finding this? Find a measure of one interior angle of a regular 10-sided polygon. How will we go about doing that? Pause the video for a moment to see if you can figure this out. So to find the measure of one exterior angle of a regular octagon, all we have to do, we know that an octagon has 8 sides, and the sum of all the exterior angle in any shape, regardless of how many sides it has, will always be 360. So the answer to the first question on the slide is 360 divided by 8, which is 45. And then here for the second question is we got to figure out what is one interior angle of a regular 10-sided polygon. Well, that's silly, right? That's just 180 times 10 minus 2. That right there gives us the sum of the interior angles. But since we're finding the measure of one interior angle, we're going to take this and divide by 10. Doing a little bit of math, this is the same thing as 18 times 8. Or this is the same thing as 144. So the measure of one angle of a 10-sided polygon of one interior angle will be 144 degrees. And that's it.